Hello and welcome to Chemistry 2341 Organic Chemistry Homework Chapter 1. So I'm going to go ahead and share my screen. We're going to go through each of these carefully and kind of show you how to attack them and what the correct answers might be. So here we go. We have them from the chapter. First one was 29, which is A, C, E, and G. So we want to look at the electronic configuration and whether or not it meets the electronic configuration of a noble gas. So when we're talking about electronic configuration, we want to do our 1s, 2s, 2p, and we want to see how many electrons are in each of these sections. So we want to first look at the periodic table. So if we look at where sodium is on the periodic table, it is in group 3-1. So that means that it has at least 1s, a 2s, and a 3s in its neutral state. Okay, so in its neutral state, if it was sodium 0, we would, let me actually pull up a periodic table here. We're looking at sodium 1, sodium neutral right here, sodium neutral would have a 1s, a 2s, a 2p, and a 3s. But we have a +1 on sodium. So let's go back to where we were done and homework. And so that means we have 2 electrons in the 2s. We have, 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p. And if it was neutral, we'd have 1 electron in that 3s. But we have sodium +1, which means its electronic configuration is 1s2, 2s2, 2p6, or that's equivalent to, if we look at the periodic table, the electron configuration for neon, which is that completely filled 1 energy level shell and the 2 energy level shell. Okay, so that being said, let's go ahead and continue on with C. Now C here is F +1. So if we look at where it is on the table, it's on the 2nd row. And so we're going to have a 1s2, a 2s2, and then a 2p. But we have to figure out how many electrons are in the p. Remember, we're going to fill those 2 orbitals first, the lowest orbitals. Again, this is sodium +1, and this is fluorine +1. And if we look at which group it's in group 7a. So it started with 7 electrons. So if it was neutral, it would have 7 electrons in its outer shell. So we would have a 7 here. But we have a positive charge. And the way to get a positive charge is to remove 1 electron. So we're going to have 7 total electrons in the 2nd shell, which would give us 5 in the p. But we have to subtract 1 electron. So that's going to give us 4 in this p for a total of 6 electrons in that outer shell, the number 2 shell. And that gives us our configuration for fluorine. Now, does this fit a noble gas? Well, no. The 1s fits a noble gas where we have the helium, and then we have a 2s2 and a 2p4. Now, that does not equate to a noble gas. All right, the next one we have here is E, so let's do E, calcium +2. And if we look at calcium on the periodic table, we see that it's way down here in the number 4 energy level. So if it was 0 charge, we would have 1 electron in each of these s's, the 4s level. But we saw that calcium was +2. So that means we have no electron here and no electron here. We have to take 2 electrons to get those 2 positive charges, which turns it up to the configuration of the noble gas above it. So we've completely filled this 3 energy shell. So let's look at how we would do that. And so that means that once we got to that energy level, we're going to say that I'm gonna draw them all out so you can see where they come from. So there's a 1s2 completely full. The 2s2 and the 2p2 will have 6 electrons in it, which makes it completely full. The 3s2 and the 3p6, the number above is the number of electrons in there, are completely full. And if calcium was neutral, it would have 2 electrons in the 4s, but it's not, it's +2. So we remove those 2 electrons and that gives us this configuration. So we've completely filled that energy level 3. So that gives us the same electron configuration as the noble gas of argon. Argon. Right here. So again, we're filling all the lower energy levels first, and then that last energy level, if it's full, then we have the configuration of a noble gas. If it's not full, then we don't have the configuration of a noble gas. All right, so let's do our last one here so that we can make sure that we have all of our ones done, and that would be letter G, which is oxygen -2. Oxygen -2. So we have oxygen -2. So that means it's going to have 2 more electrons than it had on its neutral state. So if we look at the group, it's in group 6A. So that means it should have 6 electrons in its outer shell, but it's -2, which means we have to add 2 electrons. So that means it's going to have 8 electrons in its outer shell. Okay, so let's figure out where it is. Okay, so we have the 1s and we have 2 electrons there. So then we have the 2s and we've got to put 2 electrons there. And then we have the 2p. Now we need a total of 8 electrons in this outer shell. So we already have 2. So let's put 6 more here. Now we have a filled shell. Oxygen has the electron configuration of neon, which is the filled shell, the filled 2 shell. So now we see that in neutral states, we start looking at where they are, which group they're in. If they're group 1, 2, 3, 4, or 5, or 6, or 7, tells us how many electrons there are in the outer shell neutral. But then we add electrons if we have a negative charge, and we subtract electrons for each positive charge. All right, moving on to the next question is 30. A, B, and C. So we're going to write the Lewis dot structures for these. So remember when we were talking about the Lewis dot structure, you want to put the atom that's going to bond the most in the middle. So in the case of this one right here, we are going to start with this one. And since sulfur is going to bond possibly the most because it can have more electrons in its outer shell, we're going to put it in the middle. We're going to start with sulfur here. And then we're going to have it bonded to an oxygen, a chlorine, and a chlorine. We're just going to try to get these atoms done. Okay, now let's make sure we have a valid Lewis structure. Remember, we want at least 8 electrons around most of our atoms, not all, but most of. So we're going to put 1, 2, 3, 4, 5, 6, and then there's 7, 8 around this chlorine. Okay, now chlorine is in group 7A, which means it had 7 electrons to bring to the party, which means this electron came with the chlorine, and the other electron in this sigma bond came from the sulfur. Okay, so we can do that same thing on this chlorine because it's going to do the exact same thing. And again, that electron came from the chlorine, that electron came from the sulfur. Okay, now let's do the oxygen. Oxygen is in group 6A, which means it brought 6 electrons. So it had 1, 2, 3, 4, 5, and 6 electrons. But in that first bond to sulfur, it's only got 1 extra electron. We only have 7 electrons around oxygen. So how do we get that 8th electron around oxygen? Well, we have another electron. We make another bond with the sulfur here, and now we have 8 electrons around oxygen. It brought 6 electrons with it, and it now has 8 electrons completely around. All right, so now let's talk about sulfur. Sulfur is in the middle there, and it has 1, 2, 3, 4 bonds around it. Each of those bonds is 2 electrons. Sulfur has 8 electrons around it, therefore it is complete. All right, so that is a correct Lewis dot structure for sulfur dichloride or thionyl chloride. So let's go ahead and do the next one over here. Let's do the PCl5 and I'm sorry, PCl3 right here, POCl3. So we're going to put the phosphorus in the middle again because we think it can bond the most. And since chlorine can only bond once, we're going to put the chlorines out here. Okay, it has 7 electrons already inside our shell. It only needs 1 more. It's only going to bond once. Okay, just like hydrogen, it's halogens only bond once. Now we have an oxygen here, and we know oxygen wants to bond twice. Okay, so oxygen wants to bond twice because it brought 6 electrons. It only needs 2 more electrons to share, so it's going to bond twice. Okay, now let's look at our phosphorus. Okay, so it has more than 8 electrons around. Remember, sulfur and phosphorus are the ones that can do more than 8 electrons. In this case, they have 10. So even though there's 10 electrons around phosphorus, we know that can break the rule. We're going to leave that there. Now let's put our other electrons around. Okay, so since chlorine had 7 electrons, those are its 7 electrons, and then it shares 1 electron in the bond to give us a total of 8. All of the chlorines end up with 3 lone pairs plus the 1 electron shared. So that's a valid Lewis dot structure. Now let's look at oxygen. It brought 6 electrons. That's 1, 2, 3, 4, 5, and 6. Those are the 6 electrons it brought to the party. But with the 2 bonds here, it has 8 electrons around it. It's a valid Lewis dot structure. Okay, so we see we want to make sure we look at how many electrons each atom brought in, how many times each atom should be bonding, and how many electrons around each atom after they are bonded. Okay, so let's do the last one. Let's do this phosphorus pentachloride. So again, chlorines can only bond once, so we can't put those in the middle. So we're going to put this one here. We're going to put the phosphorus in the middle, and we're going to put 5 chlorine bonds around it. Cl, 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 Cl. And just like before with the chlorines, we know we have a total of 7 electrons that each chlorine brought in. 1, 2, 3, 4, 5, 6. There. And 1, 2, 3, 4, 5, 6. So each chlorine brought 7 electrons, okay? And so it only needed 1, and it's only bonding once. So that gives us our chlorines are all satisfied having all of those lone pairs around. Now, how many electrons do we have around phosphorus? Okay, it's in group 5A, so it brought 5 electrons to the party. So it had to bond 5 times to pair up all those electrons, and that gave it 10 electrons. Okay, again, it's one that breaks the rules, but notice the bonding is slightly different than in the case with the oxygen here. The bonding was 2 bonds between the oxygen and phosphorus. In this case, all the chlorines are only bonding once. Okay, moving along to the next homework problem. Give the formal charge, if one exists, to each atom of the following. Okay, so when we have things like this, we can start with 2 things. We can look at the atoms that are different. So this oxygen is different than these 2 oxygens, but those 2 oxygens are the same. So they might have the same charge. So we'll calculate that and make sure. And then this one's different. So we have all those different ones to do. So let's look at carbon first. In the carbon here, when you do this, many times you'll see that carbon's probably always going to be 0 if it has 4 bonds around it, but let's draw it out. We have 1, 2, 3, and then a bond to an oxygen here. So our carbon was in group 4A. So let's do our formal charge thing. Formal charge is equal to the number of valence electrons in the neutral state minus the half of the bonded electrons. Hang on, I gotta pause. Our formal charge is equal to the number of valence electrons it brought minus 1/2 of the bonded electrons minus unshared electrons, okay? So we have to think about those as the ones that are in bonds and the ones that are unshared electrons. Okay, so our formal charge for carbon here is equal to 4 electrons minus 1/2 of the bonded electron. And so we have 1, 2, 3, 4, 5, 6, 7, 8, because each of those bonds is 2 electrons, so that's 8. And we have no lone pairs around carbon, so that's a 0. So our formal charge on carbon is 4 minus 1/2 of 8 is 4, which is equal to 0. So our formal charge on carbon is 0. Now, let's go on and calculate our formal charge for our first oxygen. In our first oxygen, we see that we're going to go with an oxygen in the middle with a bond here, a lone pair, a lone pair, a lone pair. Okay, so just looking at that, we have our formal charge is equal to the number of valence electrons, and it's in group 6A. So we're going to start with a 6 here, minus 1/2 of the bonded electrons. So we have 1, 2, 3, 4. So that's 4, minus, we have 2 lone pairs. So that's a total of 4 electrons, 4. So we have 6 minus 1/2 of 4 is 2, minus 4 is equal to 0. So that means the formal charge on this oxygen is 0. The formal charge on this carbon is 0. Okay, so we know where our valence electrons come from. We know which are the bonding electrons and which are the non-bonding electrons. So now let's do the 2 oxygens that were above and below the sulfur next. Okay, and so these are on my screen, at least in red, hopefully on yours as well. And we'll see that this is our formal charge for these oxygens. And they should be the same, is equal to, let's see, we have an oxygen with 1, 2 bonds and 1, 2 lone pairs. So that means we have a total of 6 valence electrons, since it's in group 6A, minus 1/2 of 1, 2, 3, 4 electrons, because it's 2 bonds. So that's 4, minus total of the number is 4. So we have 6 minus 2 minus 4, which is equal to 0. So the formal charges on those 2 oxygens are 0 as well. Okay, notice they're slightly different bonding. The oxygen is still bonded twice. So we have that. Okay, so now let's do the last oxygen, which is the one on the end. Okay, now I think our number is going to change a little bit. Let's see this. Okay, so this last oxygen right here, we again have 6 valence electrons. We only have 1 bond, so we have minus 1/2 of 2 electrons. And notice we have 1, 2, 3 pairs of electrons. So that's going to be minus 6, okay? Because we have 3 pairs of electrons. So we have 6 minus 1/2 of 2 is 1, minus 6 gives us a total charge of minus 1. Okay, so that means there's a minus 1 on this oxygen. So let's figure out what's on the sulfur, because the sulfur is here in the middle. And let's go with that here. So sulfur is in group 6A. So 6A is telling us we have 6 electrons coming in. So we have 1, 2, 3, 4, 5, 6 bonds. Okay, so sulfur is 6 minus 1/2 of 12, because we had 6 bonds. Each of those bonds is 2 electrons, minus 0 unpaired electrons. Sulfur is equal to 6 minus 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yes, 6 bonds. Okay, just double checking my math there. 6 minus 0, so the formal charge on sulfur is 0. Okay, so we can do that calculation for each of those elements and get to that. I'm going to do one more. I'm going to do the one in number B, and I'm going to leave number C there for you guys. Oh, I only have to do B. Ha ha ha. So what we're going to do is we're going to do the last one and we're going to break it down per atom again. We're not going to do the carbons because carbon with 3 hydrogens bonded to something is always going to be 0. So we're only going to do the sulfur and the oxygen and figure out where the charges lie in that compound. Okay, but we're going to do that exact same structure where we're going to start with oxygen first, and then we're going to do the sulfur second. Okay, and remember, formal charge is equal to valence electrons minus 1/2 of the bonded electrons minus all the unbonded or lone pair electrons. Okay. So we have sulfur here is in group 6A, so it should have 6 valence electrons minus 1/2 of, it has 1, 2, 3 bonds around it. So that's 6 electrons minus, oh, and it has a lone pair on it, minus 2. So it's going to have 2 there. So that means we have 6 minus 1/2 of 6 is 3 minus 2, which gives us a net of plus 1. So the charge on sulfur here is plus 1. Okay. Now let's figure out what's happening with the oxygen. And we're going to do that same calculation. Oxygen is in group 6A also, so it's got 6 minus 1/2 of the bonding electrons. It only has 1 bond, so that's 2 electrons, minus the unpaired electrons, and they have 3 lone pairs for a total of 6. So that means our formal charge on oxygen is going to be 6 minus 1/2 of 2, which is 1. So 1/2 of 1, 1/2 of 2 is 1, minus 6, giving us a minus 1 charge. So that means the oxygen has a minus 1 charge. The sulfur has a plus 1 charge. So the molecule is net 0. So go ahead and do that again, and you'll see that you only have to do the 2 different types of oxygen here. We have 2 different types of oxygen. Because they're bonded the same, they should have the same formal charge, and then do the sulfur last. All right, on to the next problem here. Add any unshared electrons to give the element an octet in its valence shell in the formulas below and indicate the formal charges. Note that all of the hydrogen atoms are attached to heteroatoms have been drawn if they are present, meaning if they're not there, if you don't have something there, those are going to be electrons. We're going to do A, B, and C. So the first thing we want to do is look for, okay, where are we going to put our lone pairs? On this one, let's see, we have 1 bond, 2 bonds, and 3 bonds to nitrogen. Okay, so that means nitrogen wants 3 bonds plus have a lone pair because it's in group 5. It has 5 valence electrons. It needs 3 bonds to fill its octet. So that 1 bond here is 2 electrons, 2 electrons, 2 electrons for a total of 6 electrons. We need 2 more electrons on that first nitrogen to get us our octet. Okay, so that covers that. Our carbons here are all going to be, are going to have octets. So all of these have octets. Now let's look at this next nitrogen here. We have a 1 bond here, a 2 bonds, a 3 bonds, and a 4 bonds, and no lone pair. Uh-oh. That means we have to calculate our formal charge. Okay, for this nitrogen here, we have formal charge is 5 electrons because it's in group 5, 5 electrons minus 1/2 of the bonded electrons, which is 1, 2, 3, 4. 4 bonds is 8 electrons minus the unshared electrons, which in this case is 0. So 5 minus 4 is equal to plus 1. So that means the charge on this nitrogen is plus 1. Okay. Now, if we did that same calculation on the other nitrogen here, we would see it has 5 valence electrons minus 1/2 of the bonded electrons, which is 1, 2, 3. So that's a total of 6 electrons minus 2 is going to give us 5 minus 3 minus 2, which is equal to 0. So the charge on this one here is 0. The charge on that nitrogen is plus 1. Okay, So we're going to move on to the heteroatoms, the atoms that aren't carbon. We're going to look at this group of heteroatoms up here. Okay, so we're going to take these one at a time. So this nitrogen here has 1, 2, 3 bonds. So it needs a total of 2 more electrons to have its octet. So we're going to put 2 electrons there. Okay, so let's look at the center nitrogen. It has 1, 2, 3, 4 bonds. Each of those is 2 electrons. It has an octet. So it's done. Okay, this one has 1, 2, 3, 4 bonds. I'm sorry, 2 bonds. This top one here has 2 bonds. So it only has 4 electrons around it. So we're going to have to put 2 lone pairs to make it into our octet. And that'll give us that structure there. Okay, so now we have to calculate formal charge for each of those nitrogens. So let's start with this one down here. We have 5 electrons in the party. We have 1, 2, 3 bonds. So 1/2 of 6 electrons minus the lone pair, which is 2. So that's 5 minus 3 minus 2 is equal to 0. So this first nitrogen has 0 formal charge. Okay, so now let's move on to the second nitrogen right here. And so we have 5 valence electrons minus 1/2 of 1, 2, 3, 4 bonds. So that's a total of 8 electrons, and it has 0 unshared electrons. So 5 minus 4 minus 0 is equal to +1. So the nitrogen charge on this nitrogen is +1. Okay, so let's do the last one right here. Let's do this last one here. And we're going to do that same calculation. And that will give us our, let's see, we have 5 minus 1/2 of 1, 2 bonds. So that's only 4 electrons there, minus 4 more electrons for the unpaired ones. So we have 5 minus 1/2 of 4 is 2. 5 minus 2 minus 4 is equal to -1. So the charge on this nitrogen is -1. Okay, so let's see if, so that means the net charge on the entire molecule is +1 because these 2 charges these 2 charges up here cancel out. And this is the only charge left on the molecule. Okay. So use that same strategy to attack B and C. All right, let's see. I'm going to do the first 2 on this one as well. I'm going to do A and B, and you'll do C and D by yourself here. Write the condensed structural formula for each of the compounds given. Okay, so the spheres in the middle are the carbon, right? So we're going to start at one end and work to the other end. So we're going to start at that. We're going to go a CH3. So that's this first one here. And it's bound to this carbon here. And so that carbon there is a CH. And then it has a CH3 down here at the bottom. And then it has a CH2 on this side. And then there's an OH is our last one. The O is always oxygen. I mean, the red one is oxygen, and then it has a hydrogen on it to it. So moving from one side to the other, make sure we have our connections correct, okay? So let's look at that again. We want to make sure our condensed form is right. We have our CH3 attached to a CH. And attached to that CH is a CH2 and a CH3. And then attached to the CH2 on the other side is this OH. So CH3, CH, CH3, CH2, OH. All right, so let's do the next one here. Let's do B. And then you can do C and D yourself. So let's do that same thing starting from one side to the other. And we're going to start with this side here. So we see a CH3, and then it's bonded to a CH, which is bonded to a CH3 going back here, going down this way. Then we have a CO, C double bond O. right here. So it can be written CO or C double bond O. I like to write it as C double bond O to show you that there's that double bond there and show you that it's bonded to that carbon. And then we come over to here, and so now we have another CH from this atom here, and then it has two CH3s attached to it. So we're going to do a CH3 over here and a CH3 over there. So that means our condensed form is going to be CH3, CH, CH3, C double bond O. No, I don't want to draw that way. C double bond O, CH2, CH3, CH3. Okay. Now, what is the molecular formula for each of those compounds? Which is the next step, okay? The molecular formula for this compound, if we've drawn it out this into its condensed form, we have 1, 2, 3, 4 carbons, so C4. We have 3 hydrogens plus 3 hydrogens plus 1 hydrogen, so that's 6, 7, 8, 9 hydrogens, 10 hydrogens, H10O. So this is the empirical formula for that. Okay. All right. So all we have to do is add up all of our different atoms. All right, moving on to the next question, and that was the next question. So consider the pair of structural formulas that follow and state whether the two formulas represent the same compound or are they some kind of isomers. Okay, so the way we look at this is you want to start from one end to the other and compare directly. So if we look at this, we have a chlorine, a chlorine. Okay, that's the same so far. A CH2, a CH2, a CH2, a CH2, and then a bromine, and oh wait, hold it. We have an additional carbon. We didn't have any other one. So these are different. These are different because one has one more carbon in it than they have. Okay, so let's look at this next one. Okay, so now we're given a condensed formula and a drawn one. So what we might want to do is draw this out. So if we have a carbon in the center, and then we have 1, 2, 3 methyl groups coming off, and then a CH2, and then a chlorine. So just redrawing this as a stick figure, it looks a lot like this compound here. So when we draw this formula into that formula, it turns out they're the exact same compound. Okay, so let's try it again, and let's look at this one and look for comparisons again. So the first thing we can see here is that we have a CH2Cl, CH, Cl, CH3. Okay, so we can draw this by saying, okay, we have a chlorine attached to a carbon with 2 hydrogens on it, which is attached to a carbon with a hydrogen on it, which is attached to a chlorine, and it's attached to a carbon with 3 hydrogens on it. All right, so we've converted this condensed formula into the stick figure. I'm going to erase this hydrogen. I was just putting it there to show that that's where it was, but I'm going to erase it so that we can see if it's the same as the other structure. So let's draw this one right here. And again, we're going to start from that same side that we started before. So we have a CH3 going to a CH. So there's an H here and there's a Cl here. That's what this next thing here, followed by a CH2, followed by a Cl. Okay, so we've gone from that left to right, and I'm going to again erase the H because we know the H is there. We just wanted to make sure it was happening. Now, it looks like if we took this compound and rotated it around this direction, they would be the same compound. Okay, so translating from the drawing to the other one is kind of important. Okay, so let's do the last one here, and we're going to draw this as a stick figure here. So we have a CH3 going to a CH2. Okay, so we're just drawing basically our skeletal structure here. And remember, if we have a carbon-carbon bond, that has to have a bend in it. So if we draw this structure as a skeletal structure, it'll draw the same compound. Okay. So see how the condensed form can be written where the carbons don't have to be in the same direction, or they can be in the same direction. But when we draw them out in skeletal form, we see that they're the same compound. Okay, so moving on to attacking homework problem number 36. Rewrite each of the following using the line bond formula. Okay, so I'm going to do the first three on the top here, and you can continue to do four. But again, the best way to do it is to start from one side. So we have a CH3, so we start with a stick, CH2 bend, CH2 bend, and then C double bond O, then a stick. And remember, the end of the line is that CH3. So that's how we would convert it from one to the other. All right, so now we have 3 CH3s on a carbon. So let's do that next one there. And so we have a carbon with 3 CH3s on it. And then we have a CH2. And then we have a CH2. So we have the first CH2, the second CH2, a third CH2, and then an OH. OH. Okay, so let's see if we have that. We have 3 carbons here on one carbon. So we have 1, 2, 3 on the central carbon. Then we have 1 CH2, 2 CH2, 3 CH2. 1 CH2, 2 CH2, 3 CH2. OH, OH. So our final line structure is OH. All right, so let's do this last one here. And we're going to start at the end here. And so we have a C double bond C. So then we have a CH2, a CH2. So that gives us 2 lines like that. Then we have a C double bond C. And then at the end of that, we have a methyl group. So we have 1 more carbon to add. So starting from one side or the other, make sure that you have your double bonds in the right place and you count the number of CH2s. Each CH2 counts as an inflection point in your line bond drawing. Okay, write the line bond drawing for all the forms of the constitutional isomers for C4H8. Okay, for C4H8, that means we're going to have a total of 4 carbons and a total of 8 hydrogens. So 1, 2, 3, 4. Okay, do we have 8 hydrogens? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, that's 10 hydrogens. So we have to have less than that. So the easiest way to get rid of 2 hydrogens is to make a double bond. Okay, so now let's count our hydrogens again. 1, 2, 3, 4, 5, 6, 7, 8. So now we have 4 carbons and 8 hydrogens. Okay, I'm going to take away those lines because we know that the hydrogens are there now. Okay, actually, let me go ahead and put that first structure up there with all the hydrogens on it. So we have C3, CH2, C double bond C, HH2. So we have hydrogens here, hydrogen here, hydrogen there, hydrogen there, and 3 hydrogens over here. Okay, so that's the first one. Okay, so what I'm going to do is I'm going to take away the line and we're going to do line bond formulations because that's what we're asking for here, a line bond formulation. So, all right, so the first one's going to be do, 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 do. Okay, so then another possible isomer is just move the double bond do, 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 to the middle. Now, if we move the double bond to the other side, that's exactly the same as this one. So these aren't isomers, it's the same compound. So what else can we do? Well, we can take that methyl group right here and move it over a bond and see if we can't get a different isomer. So if we do that, double line with that, ooh, that gives us a different isomer. So like I said in class, when you want to do these kind of structural isomers, start with the longest chain you can and then start chopping it and moving stuff around. Let's see, there's got to be one more isomer here somewhere. Oh, I know what we can do. We can draw one more isomer it has the same, oh, wait, hold it. We can draw another isomer. All right, so this has 2, 4, 6, 8 hydrogens on it. So it's 4 carbons and 8 hydrogens. And this has 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 4 carbons. So let's see, that seems to be, let's see, what other isomers could we do here? Because if we move the methyl group over there, that's this structure. And if we move this methyl group over here, that's this structure here. So we can't do that. We've already moved the double bond to the middle. And we've seen that we can have that those two hydrogens go away with rings or double bonds. So I think that's all that we can do there. Okay, so when you attack this, start with the longest structure first, and then start breaking it into smaller things. Okay, show the curved arrows to convert A to B. So this is when we're talking about moving electrons. And so those moving electrons with those curved arrows gets us to see where they're happening, help us envision where they're going. So let's see what's changed. Okay, there was a lone pair here, and that lone pair, and there's a double bond here, and there was a single bond. So remember, when we're doing resonance structures, only electrons move. And the most common things we're going to see are pairs of electrons coming in to form a double bond and double bonds coming out to form lone pairs. So let's see if we can move the electrons back and forth. So we're going to move a lone pair in to form a double bond. Then we're going to have to see where it goes from there. So I'm going to start with the one on the left here. And I'm going to say we are going to move these electrons in here. Okay, that gives us our double bond. Okay, but this double bond is not in the other compound. So that means we have to move these electrons up. Okay, but there's a double bond on the other side. So we're going to move these electrons down to give us our double bond on the other side of the nitrogen. But there was a double bond here. So these electrons had to move over here. Oh, but there was a double bond here. These electrons moved over here to give us our charge on our oxygen. So to get the charge, these electrons to go from here to there, we had to move 1, 2, 3, 4, 5 pairs of electrons. And when we move those 5 pairs of electrons, notice we went from a neutral compound with no charges to another compound with 2 charges. Okay, so that way, number one, they are resonance structures of each other, no atoms moved, but this is the slightly more stable resonance structure because there are the charges. This is the slightly less stable because there are charges, but they are resonance structures. All right, so moving on to number 41. Now we're going to talk about drawing resonance structures. And I'm going to do two of these for you, this one and that one. So let's see, we have a double bond here and an oxygen and 2 lone pairs. And we want to draw a resonance structure to give you something. So a really common thing that we see is lone pairs and double bonds moving around in our resonance structure. So let's see, one possible resonance structure is we could have these electrons come in and these electrons pop out, giving us oxygen with a double bond here and a lone pair on the hydrogen out here. That's going to give us a negative charge on carbon and a positive charge on oxygen. Now we still have 1 lone pair on the oxygen because we only moved 1 of the lone pairs in. So that's a possible resonance structure for that. Let's see, could we do it the other way? Could we move these lone pairs out? No, because we'd have too many bonds to carbon. Now we have 3 hydrogens here, and that would give us a total of 5 bonds to carbon. So we really can't move it that way. We still only have 3 bonds to carbon on this side and a lone pair. So it has that negative charge. All right. So do we see how we're going to be moving those electrons in and out? We're going to usually move them with or without changing a double bond. So I'm going to do this last one here. D as our last example for this one. Erase objects. And we're going to see what that does here. And so we're going to start with a lone pair on, two lone pairs on the oxygen and one lone pair on carbon with a negative charge. And we're going to draw a resonance structure for it. Okay, on this resonance structure, we're going to see it go, well, let's see, we're going to have these electrons come in and these electrons come out. And when we do that, we get a double bond here, and we have a single bond to oxygen, but we have 3 lone pairs giving us our negative charge here. Okay, so let's see, would the electrons come over here? No, because we remember we have 3 hydrogens over here, and that would give us 5 bonds to carbon, so we can't do that. We'd have to move a hydrogen, so we can't go that way. So we have to go the other way, and when we go the other way, we can move the electrons onto oxygen. Now, which of these is the more stable resonance structure? Okay. Okay, remember that when you have your charge on the negative charge, on the more electronegative atom, it's more stable. So this is going to be slightly more stable than this one here, but they are perfectly valid resonance structures. All right, so now we're going to go for 150, the last one right here, and we're going to do A, B, and C. I'm going to do A and B, and you guys are going to do the last one yourself. So the way to attack this is to look at the structures, to find the relationship between them, and say what they have. Okay, so let's see. In this case here, let's draw it with all the hydrogens present. H, H, and then nitrogen with a positive charge, which means it has H, H, H. It has 3 H's on it right here. And then we have a hydrogen here. Okay, so that's just drawing this first structure with all the hydrogens there to make sure we're not moving anything. Okay, so now let's look at this one here and draw that. We have 3 hydrogens on the carbon at the end. We have a double bond to the nitrogen now, not to the carbon. We had a double bond to carbon on this side. We now have a double bond to nitrogen on this side. And we have a hydrogen here and a hydrogen here, and we still have a positive charge on nitrogen. Okay, so what's the relationship? Are they constitutional isomers or are they resonance structures? Well, the first thing we notice is that there are 3 hydrogens on this carbon and 2 hydrogens on the equivalent or the same position carbon. It can't be a resonance structure. We've moved an atom, okay? So that makes it an isomer, a constitutional isomer, because we've moved an atom. We've changed where the double bond is. It's now between the carbon and the nitrogen, versus on the left side here, the carbon and the carbon. So they are isomers of each other, and they are structural isomers. Okay, so I'm going to do B next and say, okay, line drawing. So let's convert this into a line drawing. So we have a CH3, and then a CH2 is our bend, a CH2 is our bend. So 1, 2, 3, another CH with 2 methyl groups on it. So that's 2 methyl groups on it. See, there's 2 methyl groups. So we're going to do CH3 is the end here, CH2, bend, bend, the CH. Oh, I added an extra CH2. That's okay. Let's do CH2 and then 2 methyl groups. All right. So now let's take away that and let's make sure that's the right atom. We have a CH3. So that's the end group here, a CH2 there, CH2 there, a CH here, and then 2 methyl groups. So we have drawn the right structure. We double checked it. And now we have to compare it to this other one. And if we rotate this around this way, we'll see that they're exactly the same isomer. All right, thank you very much. And hopefully this gives you a way to attack these homework problems for your chapter 1.